key idea of the paper is to go from RGB images of a scene to a complete 3D volumetric representation of the world that also has panoptics in them.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Panoptic Lifting for 3D Scene Understanding with Neural Fields. This paper was published in CVPR 2023, and I am happy to host the first author of the paper, Yawar Siddiqui. Hello and welcome to the podcast. Can you introduce yourself?
Hi, it's great to be here. I'm Yawar Siddiqui, and I'm a PhD student with Professor Matthias Niesler at TUM. And I'm going to be presenting this paper, Panoptic Lifting, which was a highlight at CVPR 23 this year. And we did this in a collaboration with Meta. So it was an internship at Meta last summer in Zurich. And apart from me, we had Lorenzo Porzi, Samuel Rotapolo, Peter Conchita from Meta, and from TUM we had Norman Mueller, Matthias Niesner, and Angela Dai.
Okay, so in a TLDR kind of format, what is this paper about?
So the idea of the paper is that given only RGB images of the scene, so only images taken from a camera around the scene, you optimize a neural 3D volumetric representation. And once this representation is optimized, you can render it from novel views. And when you render it, you can render the color, you can render the depth, you can render the semantic segmentation, the instant segmentation. So the complete panoptic representation of the scene. And the key part here is that you're not using anything except the RGB images, at least as an input to the method.
Really interesting. And I think like you mentioned several kind of components or keywords that we're going to break down in the approach section. But before we do that, let's dive into the introduction. So what problem is this paper addressing?
So in this paper, we're trying to solve panoptic 3D segmentation, but in a neural field setting. So let me first say a few words what panoptic segmentation is, because we're going to be using this again and again. So in a very vision sense, you can, like, to make it easy to understand, you can say it's semantic and instant segmentation taken together. So panoptic as a word basically means everything at once. So it's semantic understanding, instance understanding all taken together. But there's, like, if you get technical about it, it's also about the concept of stuff and things. So you cannot have instance segmentation for everything. For example, there are no instances of sky. There's no instances of floor. So for these things, we call them stuff. And then there are things that are countable, like a sofa, a chair, or a table. And these are the things. So panoptic segmentation is breakdown of stuff into stuff and things. For things you have instances, and for others you have semantics. So all of this together.
And does that relate a little bit to kind of foreground, background items in some way? Because
it is in a similar way, but maybe more here in terms of countability and if it's countable or not, and whether it makes sense to have an instance or not. And a lot of times it's up to, like, the method to decide what's going to be a thing and what's going to be a stuff. And there's also some some leeway we take in defining what's stuff and what's things. But anyway, so you were asking more about what's the problem we're addressing. Yeah, so we're trying to solve panoptic segmentation for neural fields, and we also want to not actually have the user label this stuff out. So make it easier in terms of input-output setting. So how much the user has to do here.
So, can you just for a second pause and say what are neural fields for those that don't know exactly?
So neural radiance fields, or NERS, is this great representation that came out around 2 years ago, and we have so much work in this now. So it's basically a way to capture implicitly a scene in such a way that, like, for each point in space, you can capture the radiance of the scene. And the way it's done is rendered volumetrically to an image. So there's sort of ray marching through the scene, and you accumulate the radiance, and you can then render to an image. And I mean, it was proposed for the novel view synthesis task initially, but there have been a lot of derivative works leveraging it for different tasks, and we're just another task is like using the same representation in for panoptic segmentation.
So maybe in other words, we have a network, right, that we can use in order to kind of model the entire space or like some 3D space in such a way that at every point we get a density and RGB, right? Now, if we have for every point a density and RGB, we can project it onto an image and get like this nice rendered image, even of things that we haven't seen before. This is why it was used for novel view synthesis, right?
Exactly.
In your case, you're using it for an entirely different problem, right? You're saying, okay, now I have this volumetric kind of representation, right? I know what happens everywhere in space. Can I know more about it? Not just the RGB and density.
Exactly. So one other thing I like to think about is neural fields are just another representation of a 3D scene, right? Like just like you had meshes, and you can render them to images, right? In a similar way, there are like segmentation on meshes and other 3D representation like voxels. In a similar way, think of neural fields are a representation that are being rendered to images, and now we add segmentation, panoptic segmentation to it.
Okay. So you were starting to explain what the problem that this paper is addressing, and we paused for a brief overview of what is panoptic and what is neural field. Okay, so what is the problem here?
So the thing is, 2D. So why we got into this problem is we saw that 2D segmentation networks are actually quite good. So if you take mask to former or now segment anything, like these methods work really well. And also on images that you take in the wild, right? Like if you take a picture from like this scene where I'm sitting here, you can segment everything pretty nicely. But the same kind of results are hard to get in 3D. So if I take a couple of images from this scene, and run it through these kind of models, you start to get a lot of issues. So you'll start to see that like for the same object in different images, you might get different labels. Sometimes the model just fails to predict anything. And also you cannot really use these 2D models for instance segmentation because the ID gets counted again and again, right? So it has no notion of two different frames and two objects being the same in space. So it will just count them again. And so we want to see what's the most effective way of leveraging these 2D models, which are already so good, and lifting them up to 3D representations. So that's the problem we're trying to address.
Hence the name Panoptic Lifting.
Panoptic Lifting, yes.
Okay, but why is this an important problem? Like, why should people want to do this?
On a more like high level, I guess it's one of like segmentation is one of the most basic vision problems, right? Like a lot of downstream tasks come from it, and like we're only recently seeing all the interest in like novel view synthesis and all that. But like original vision problems were segmentation because you see like there are a lot of applications like I don't know augmented reality, virtual reality, robotics, so robot navigation where it has to go. Like if you have to tell a robot to pick something, you have to know what that is. So self-driving cars, for example, need to know what's there on the road. So all this segmentation is like a really basic vision problem, and it just opens up a lot of ways, like a lot of downstream tasks. What's also like in our paper, we actually show a small downstream application, which is editing of the scenes, but that's just a proof of concept. Like I think segmentation on its own is a very important core problem, but we also show some downstream tasks in the paper.
Yeah, I can totally see where this comes into play in a lot of different kind of applications. So really interesting direction. But what are the main contributions of this specific paper?
Okay, so as we put it in the paper, we can make it into two parts. So one is going from only RGB images to this 3D representation where for each point in the scene, you can have the color, the density, the semantic, and instance IDs. So this is all coming from 2D machine generated labels. So that's one part. And the second part is, since we are using machine generated labels, they tend to be very noisy. So if you just naively go ahead and do the first part, you're going to get a lot of noise, you're going to get a lot of issues. And these are some things we highlight in the paper if you naively do this. So how do we handle this and make it more robust so that it actually works with machine generated labels?
Okay, I can't wait to dive in deep into the approach. But before we do that, let's talk about related works. So which one or two papers should people read before reading your paper?
So one thing, as you point out at the start, right, like here, that what are neural fields? People have to know this because we're using it as a representation. So NERF is a really inspiring work in this field and very fundamental. Then as a backbone, we don't actually use vanilla NERF, but we use a paper called TenSurf, which makes NERF faster by factorizing it into these triplane-like representations. And this is also important since we're using it as a main representation. So these two are really like foundations. On top of that, we're using this 2D model called Mass2Former. It's nice to know this, and I think this is what makes our thing work. If this didn't exist, I'm sure this wouldn't have worked. Then more related to our paper, so more related work would be semantic NERF, which was like when NERF came out, I think one conference later, there was semantic NERF, which was doing it with, so how do you add a semantic field to a NERF? And they did it with like complete ground truth masks and like really ground truth info. But nevertheless, it's like a fundamental work in this domain. There's also panoptic neural fields, which is a paper from Google, which is super related. And it does things, I think it actually solves exactly the same problem, but in a different way. And maybe we'll talk about why we felt the need to make another paper in the same domain.
Yeah, in order to break that down, we have to start talking about your papers. So how did you do it?
All right. So let's again talk about the input-output setting. Okay. So in the input, you have RGB images of a scene, right? And in the output, we want this panoptic field representation that can be rendered to all these semantic, instance, and color images, right? So
should note pose the images, right? You know where they were taken from as well.
So I don't say pose because it sounds nicer to just say RGB. And pose calculation is part of our post processing, like all the NERF papers. So I just don't say it because it sounds nicer. But yeah, you're right, absolutely right. Like you have to have poses.
Right.
So as a part of pre-processing, we do two things. As you said, like we create poses with Colmap. This takes a little bit of time. And the second thing we do is we run Mass2Former to get, for each of the input images you captured, the semantic segmentation and the instance segmentation. And we can go ahead and optimize the field and everything. But before we do that, while inferring with Mass2Former, we also make sure that instead of like getting just one prediction out of the network, we make like multiple predictions out of it. And the way we do it is like this technique called test time augmentation, which is basically instead of taking the same image, you kind of corrupt it. So maybe you stretch it out, maybe you add a little bit of Gaussian noise to it, maybe you flip it horizontally. So you take the same image, run it multiple times to the same network, and now you have a distribution of outputs, right? Like, so you have a distribution of semantic segmentations, you have a distribution of instance segmentations on the same image. And this is just helpful for something we'll do later on, right? So yeah. So once we have this pre-processing done, we have the poses and the segmentations, we now want to optimize a neural radiance field out of it. So NERF already gives you a way to get the color field, so the radiance field and the density, right? Like, so it's an L2 loss. You just sample points, sample rays on the images that you already have. You have this accumulation along the array of densities. You get the pixel out. You have a normal L2 loss. This is all typical NERF stuff that we also do to get the radiance field out. This kind of handles the density and the RGB. Now, how do we model the semantics? And so we simply add to TensorF, which is a triplane representation, we add like a small MLP to handle semantics. So it's an additional head. It's an additional field basically that renders semantics. And the form it takes is for, let's call it probability of this particular point to belong to a certain class. And this class set is fixed beforehand. And we have another, yet even smaller MLP for instances that determines for each point in space to belong to a certain instance ID, let's say, right? So optimizing the semantics is again kind of simple. So you just render, the way you render RGB is, right, like you're accumulating stuff in 3 channels, but now you accumulate the probabilities in more channels, which is the number of classes, and then you have a certain cross entropy loss at the end. The instances are harder because you don't really have the supervision, right? Because the instances that you're supervising with are coming from masterformer, which keep changing their instance ID all the time, right? So you cannot directly use them because, I don't know, if this jug exists in one of the frames, might have gotten an ID of 2, but you see it in another frame and you might have gotten an ID of, I don't know, 5. So you cannot really supervise with it. And like kind of the like intuition is that nerf kind of gets the depth right during the optimization. So it will have an idea of what points in space might have the same ID, right? So we take use of this fact. And another fact that when the images you're getting from masterformer, let's consider just one of the frames, right? For instances, what information do you get from this? Like if you see one image from masterformer and the instances, the only things you can infer from this is things that get classified as a single instance. All the rays belonging to a single instance are the same, right? Like this is what you know for sure. And the other thing you know is that if 2 things are classified as different instances, these rays are belonging to different objects. So you can infer about a single frame, but if I give you 2 frames, there's not much you can infer. So for 2 frames, you cannot say if 2 different rays belong to the same or the same different instance. So typical NERF optimization, it just samples rays from all over the frames. It's not necessary that you sample rays from the same frame. But for instance optimization, it's really necessary that you sample rays from the same frame because the information is only valid within the same frame, right? So the next step we do to supervise...
Wait, before we go on to the next step, I feel like there's a lot to take in, so I want to break it down a little bit. Okay, so first thing you said, pre-processing, right? You get a bunch of images, you get their poses, you get their segmentations, and not only you get segmentation, you get probabilities as well, right? That's the first part. Now you feed that into your NERF, but oh wait, NERFs are just RGB and density. Oh no, here's where you come in. You say, okay, we take another MLP. This additional MLP will give us the segmentation and instances. So far, it's fine, right? You can get the segmentation okay, not too hard, right? You use a specific loss for that. But the instances, that's where the challenge comes in, because if you take different views, the instances are a mess. So you kind of have to handle it in a smarter way. And your smarter way is to kind of focus on the like rays from a specific frame to overcome that bit.
Yes. And okay. Exactly. Like this is a really good summary. So the instance part is the more challenging part. And the thing is, you have to map from the space of labels in a single frame. So this is like a new labeling, right, per frame, and it's going to be 0, 1, 2, 3 or something. That's the masterformer labeling. And you want to map it to the space of something that you're predicting right now, like your 3D instance IDs. So there has to be an association from the 3D instance IDs to, the 2D masterformer labels, that's per frame, to your 3D instance IDs that are existing in like the global context of the scene. And the way we do it is we used this Hungarian algorithm, so some linear assignment matching from the distribution of what we're currently predicting. So, what's the most probable label, a mass to formal label, would be associated with in 3D? So, you can think of it as like if I render the current frame's instance IDs through the nerve, and at the same, so this will give you an image, let's say, and if you look at the instance predictions from mass to former, and now I try to like overlap them, right? You can imagine what's the most probable association there, right? Like for this scene, it's probably like some big blob here, and the clean blob from master former. That's probably the ID that gets assigned to me as an instance. So that's the kind of like, so using these, we don't use IOU, we use probabilities here, but it's, think of it as something like a soft IOU. We create like a cost matrix for this Hungarian matching algorithm, and we perform this matching. And this gives you a mapping going from master formal labels to the 3D instance labels. Now we're in the same space. So for the 2D frame, we actually have 3D instance IDs, and we can actually use like a normal cross entropy laws that that's typically used, and that is used to supervise it. So that's one part. So this does some sort of a job, but if you just go ahead and do this, there's a lot of issues. So both in semantics and instances, because the labels that if they were coming out to be perfect, this would have worked already, but they're usually noisy, right? So as I said, like different frames, it's machine generated labels, right? Like so there would be some noise because it's not quite the ground truth. Yes. So how do we handle this noise? So one thing is, I mentioned before that we were taking multiple test time augmentation runs. This also gives you a sort of confidence scores for your predictions. So you can weigh your losses by these confidence metrics. This helps a little bit. What also is a problem is if you so this is actually very specific to neural fields, because I don't know if you remember, there's this issue of floaters in neural radiance fields. So sometimes when you can't really like explain something, you make up floaters to explain it better. And this using semantics, so supervising semantics can have a really strong effect on floaters. So imagine that you're seeing this jug, let's say, right, from two views. And in one of the views, this is predicted to be a jug, but on another view, let's say it's predicted to be a bottle, right? Now, what is the network gonna optimize it to be? Because both of them are equally weighted, let's say, even in terms of the confidence that's coming from the network, it's equal. So, or let's say, okay, 80%, 20%, right? Even let's give it that. So the network has to satisfy both of the labels for the loss to be, let's say, minimum, right? And what it ends up doing is it, from one of the views, it will do it properly. So it will be a jug, but from another view, it will create a cloud in front of it that will say it's a bottle. So it looks good from this side, it looks good from both sides, loss is zero, perfect. So, but this is not what we want, right?
Semantic floaters.
Yes, it's exactly this. I never thought about this word, but it's semantic floaters. And visually, they don't look so bad because they're really thin. But in the semantic class sense, they do appear in the semantic mask. So what we realized is a lot of people have this debate: do semantics help the visuals or not? Right? Like, if you have the perfect semantic understanding, would it help the reconstruction of the colors and everything? And we found, like, at least in the noisy sense, it never helps. It actually destroys it. So what we say here is that, like, never propagate gradients back to the density from the semantics. And this is one thing we do. And this kind of fixes this issue. But now if we run this, what will happen is there will be no floaters. It will be perfect depth. But as you move across the scene, it will just turn the label from a jug to a bottle. And it's like, what's happening now? And we saw that, okay, the formulation everyone uses for neural fields is especially in semantics. So we're like coming from the semantic nerve, panoptic nerve background. So we were just using the same formulation as them. And we saw that they render, like, what do you output at the end of your semantic MLP? Is it logits, which nicely fit to like cross entropy loss and PyTorch, or probabilities? And we make a decision to do probabilities just because when we had used logits, this is what was happening. As you move, it's just changing the labels. Because, you know, um, when you render something, you're doing a weighted summation of all the values, all the points along the array. And as you do this, and you have logits at each of the points, these logits can go from anywhere from, like, I don't know, to infinity, right? Like they're not bounded. And what the network would do is, for this, it's fine. Like there would be a strong logic that says it's a jug at the end. But for the other array, from looking here, the logic at the surface is saying it's a jug. And somewhere in space, there's a logic that's really, really high that is saying it's a cup, but the weight associated with it is really, really low. So if you do a weighted summation of the logits, it's going to say it's a cup. If you do a weighted summation of the radians, it's still going to look at the jug. So everything works out in RGB, but it just seems to flicker in the semantic space. So basically, like the key takeaway here was, like, if you're ever rendering something with radiance fields, make it bounded, because the weights can just like mess you up. So this was another change we did. Then there's like, in the same scenario, there's still an issue, because if you think about losses, the optima is still something that's a combination of a jug and a cup, right? Because it's not one thing or the other, like, I don't know, GAN losses that promote this, but the optima of the cross entropy loss is like something of a combination. And we introduce another loss here that says, oh, we also have these instances. And actually, like, masterformer gives you segments. It's a more basic concept. So how it works is, first it makes segments, and each of the segment is assigned a class and an instance. So think of it as the floor might have different segments of floor, but it's the same class, but you won't have instances for it. But for the couch, a segment and an instance is the same thing. So we also have these segments. And what we know is all arrays belonging to a segment should be the same class, no matter what the class it is. So in both the frames, in the jug frame and the cup frame, whereas both the frames are saying it's the same thing, but whatever it is. And this we use just as a regularizer to say that it should not be a mixture of things. In each of the frames, it should be the same thing. So that's just an additional regularizer added on top. And this also helps a lot with like keeping this consistency. So if you when you combine all these things, it ends up being like this really robust and something that works with machine generated labels in the end. Yeah.
Okay, so you've mentioned a lot of different losses. Let's kind of just word title, key point, just the general name of the loss that you introduce here and what it does, right? In 2 words. So you have the regular nerf, RGB, and density losses, right?
Yes.
That's one. Then you have
the one I just mentioned was the segmentation consistency loss, which is just saying that it should be a single thing. Then you have the blocking of gradients so that you don't have these semantic clouds. And then you make sure that you're rendering probabilities on the array and not logits. And
right.
Of course, you have this whole thing where you're handling the instances by Hungarian matching.
Yeah. Okay. I have to admit that while reading the paper, the part about the losses, I had to read multiple times because each of them is talking about a very specific problem and the solution that you propose to it, and it kind of takes a minute to understand these things. So, but I think we did a good job covering them. But definitely, this is a part to go back to the paper and read it through, read through the math, understand the intuition.
And also, like, one comment here I would have is that it's a combination of a lot of things. And I think you can see like how it worked out. Like you start doing something and you think it would work, but then it doesn't just quite work as good as you want. And then you add one more thing that makes it better. Then you add one more thing, it makes it better. I think in the academic community, we don't really like this, but what I really like here is that in the end, you have something actually working in a decent way. Yeah.
Yeah, actually, like I think one of the figures in the paper, which is one of my favorite figures, shows exactly that, right? You kind of show the results without all component, then you add one component, that's how it looks, and then another component, that's how it looks, and then another one, and then oh look, it works amazing. I really like that figure. Which kind of brings us into the results section of the paper. So, what experiments did you do?
So one thing, you already made a really nice comment, right? Like this ablation thing was really important for the paper because we were doing so many things. It's important to show what works and what how much it contributes. So we show like removing each of these components individually, how much does it harm the performance, and something that's like actually visible. In what way does it harm, right? So as I said, like the semantic clouds are something very particular if you don't block the gradients, and this complete flipping of the labels when you use logits, or like coming up to a compromise that's two labels at the same time for an object. So we do all these ablations to show the effect of each of the things we do. Uh, I think that's one of the important experiments. Then the comparison to baselines here is really important because, as I said at the start in the related work section, there's a Panoptic neural fields paper from Google last CVPR that does exactly the same problem. And the issue with this paper, actually, we started with in the start of my internship, I was implementing this paper because there was no public implementation. And this is how this paper came out to be. So what we were observing there was it's really great when you have good bounding boxes to begin with. So they need, just to have a small recap for their paper, in their input setup, they pre-process. Also, they only take RGB images. They pre-process to get poses, and they pre-process to get semantic masks, and they pre-process to get bounding boxes. So 3D bounding boxes for all the frames. The issue is like if the bounding boxes are correct, it's great. Like it's a really good paper. But in real life, you don't get good bounding boxes. And that's the problem with, like, if you compare 2D and 3D networks, you'll just find that 2D networks tend to be much more robust, right? It's just more data to be trained with, and I guess a longer history of research. They tend to be much more robust. So relying on 3D bounding box detector is kind of the failing point there. And we saw that once, like, I don't know, if you miss out on a detection, like you can never recover the instances or the semantics of that thing just because of the formulation they had. So it was really important for us to compare with this method in the indoor setting we have. It's also, we also wanted to give them a fair chance that what if we run Panoptic neural fields with a perfect 3D detector, but with noisy semantic masks, right? So just to give more of a fair shot. And this is also one comparison we show in the paper. And one cool, so apart from these comparisons and ablations, one cool application we show is, let's say you just optimize your whole scene, right? Like, let's say you're done optimizing your scene. What do you do with it, with this Panoptic understanding? So we show scene editing as an example. So now, since you know what's a chair in the scene and also the individual instances, you can actually say, like, let's delete this chair. And you can do this in neural fields by just saying that wherever at a point in space you have the instance ID of 1 with chair class, delete this. Like, don't have any density there. It just disappears.
Density 0. Okay.
Density 0. And let's say you have to move it. You just say, or duplicate it. You just say that at a new box that I give, just copy over the density and the colors from this point. And so basically, like, just warping.
That's really cool. Yeah.
So this looks actually really nice in the visuals that you can just edit this out. So typically like scene editing papers, what they do is like they ask the user to mask things out, and we're just basically getting these masks from our pipeline. So that's what we wanted to show. Yeah. And
yeah, they're really nice.
yeah,
I mean, it works like physically, right? It moves it,
yes.
let's say, in the neural field domain, but it doesn't change the lighting accordingly, right? It will still have some limitations, but I think it's a really cool application.
This is true, and this is like more of a limitation of neural radiance fields, as you said, right? Like if you take the thing out of the context, it just doesn't look right because the lighting is just baked in.
Yeah. Okay. So, but this is it's not a tricky question, but it's I don't know. Some people don't want to talk about it. So when does your method fail?
Okay. So there are failure cases where the nerf optimization doesn't do well. So there are some scenes, quite a few scenes in ScanNet, because the original ScanNet was not made to be for neural fields. So you'd see that there are scenes where the nerf optimization doesn't just work so well. And since we're basing heavily on the depth priors that nerf gives, it's just completely failing there. Then another strong issue with our method is like in all the scenes we show or in the wild captures I have, we don't have dustbins because mass to former does not detect dustbins. So like more generally, the limitation is that you cannot work with classes that are not in mass to former. So we actually map them to ScanNet classes, and some of the classes just don't exist, and it just doesn't work on these classes. So that's one big limitation. Another thing we don't point out in the paper, but like it has to be said, right? Like this is a work for static scenes. It cannot work for dynamic scenes. And actually, like one of our baselines, this Panoptic Neural Fields paper actually also works for dynamic scenes. So that's actually one important point that one should say.
We'll talk about this more in the future work section, I guess.
Yes.
Were there any unexpected or interesting findings?
So I was surprised at how good these 2D networks already were. One interesting part was seeing how good the uncertainty correlated with bad results. So if I also render out the uncertainty for like these networks on how confident they are for each of the labels, like visually you see how good of an indicator this is. And this is like one potential we didn't quite leverage, but we can also talk about it in future work, but this is like kind of was really surprising to me how strongly correlated these two were. So there's definitely some more things that can be exploited there. Yeah.
Okay, moving on to the conclusions and future work section. Actually, I'm going to start this one with the future work section before I ask the usual questions. It kind of begs the question, like you're really relying on these 2D methods to lift them up to 3D, but do you think there's an option of kind of doing this in a, let's say, kind of circular or updating way, right? Or like iterative way, right? You get the segmentation from 2D, you lift them, then you get something more consistent in the 3D, you update the 2D, maybe you retrain the models or something like that to get a better, right? This could be used in this, is this something that's plausible or thought about it?
So we didn't think about it much, specifically because like these, it's an optimization setting at the moment, right? Like we have to take a lot of images and it takes 24 hours to optimize the whole scene. So the cycle would be too long to feed it back to 2D. But I can see as these nerf methods get better, and there are some methods that actually work with multiple view and do a forward pass to get stuff out. Once you have these short cycles, there definitely should be some way to actually loop it around. Yeah.
Mm-hmm. And also another question, this kind of maybe related or future work part, right? You're using an off-the-shelf segmentor, right? This could be easily replaced with the next top top scoring one. I don't know, segment anything, everything.
Exactly. So really good point. Like this was what I was gonna say. Like since you were asking, like, oh, what's the future work? And I think this is what some people are doing. They're trying to. So one limitation I mentioned is like I'm limited to the classes that master former has, but something like segment anything doesn't have this limitation. So it's very natural to replace. I mean, when we did this 1 year ago, there was no segment anything, and the best thing was master former. But now it makes a lot of sense to actually just use predictions from some top of the shelf model instead.
Right.
Yeah.
Okay, but now for the traditional conclusion and future work question. So how do you see the impact of the paper going forward? And has there been some interesting paper that followed it?
So in terms of follow-ups, I think there was one interesting work from Panoptic Lifting Panoptic neural field authors that did work in the same domain, but I think it's also kind of concurrent, so they don't quite compare with us. So in terms of exact follow-ups, I don't think we have any yet, but I know some people who are working to get segment anything working on this, and there are already some like not papers but implementations out from hobbies that try to make segment anything work with this. And as an impact, I don't know. It's a hard one to answer, I guess.
Yeah, time will tell. I mean, we never know, right?
Yeah. Yes.
Okay, great. So before we wrap up, we're moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments you had in the review process.
Yeah, I mean, we were really lucky with the reviewers in this paper, actually, like better than I expected. So they were really, really positive. One really good comment from one of the reviewers was that we're using this TensorFlow backbone, and maybe all the benefits come from TensorFlow. And actually, it was the opposite. The only reason I was using TensorFlow to begin with was to have a faster optimization, and we even used a really bad version of TensorFlow, like the easiest, like cheapest one. It was nice for us to see ourselves. Like if you just replace this with a vanilla nerf, what happens? So that was a good call. But there were also like some funny reviewer comments. So one reviewer was really, really happy with our video. So he was like, oh yeah, this was one of the best presentations I saw. And the comment he had, like what he really liked was that for the semantic masks, I was using, like whenever there's a class change, there's a black line, so a border for each of the classes. And he was really a big fan of this, which was funny seeing in a review, like, okay, yeah, this looks really nice as a strength.
Aesthetic comments.
Yes, yeah. Aesthetic comment. Another comment was like, oh, why did he choose lifting as a name in the weakness?
Yeah, I mean, when you first read it, it's like,
yes.
Wait, what? Lifting? Lifting what? Are we lifting what? Yeah. And then once you read it, you say, oh, okay, you're lifting that. Okay, then that makes sense.
It's a valid question, to be honest. Like it's just funny seeing it in the review, because like some of our co-authors, like it was like two-sided. Like some didn't like lifting, some liked lifting. So yeah, could see it.
Okay, excellent. Yeah, well, thank you very much for being a part of the podcast.
Thank you so much for hosting me. It was amazing.
Yeah, thanks. Well, thank you for being here. And until next time, let your papers do the talking. And now for a word from our sponsor. Are you interested in 3D and AI? If so, the team at Yum is interested to hear from you. Yum is an Israeli startup dedicated to volumetric video creation. They were voted as the 2022 Best Startup to Work For by the Duns 100. Join their team that works on geometric deep learning research, implicit representations of 3D humans, nerfs, and 3D 4D generative models. Visit yum.com. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.